about internal forces, and then from that we learned about how to get stresses, and we found out there are two types of stress that are more important, that are there. That is, one is normal stress that we need to find out, and the other one is shear stress, right? This is what we learned. Then we also learned how to get strains, what are strains, and similarly we learned about normal strains, and we learned about shear strains. We also learned about engineering strains and tensile strains. We also learned about strain deformation relationship, right? How to get strains from deformation. That is also, if given a deformation, how do you get strains? Are all we know. We also related strains and strains using constitutive relationships. And we all learned these things. Now, today's class onward, we will apply all this theoretical understanding that we have into various kind of members. So first member that we will apply is an axial member. Okay, and then we will go to torsional members, and then beams on bending, right? These are the three are the main part of this course, and these three will comprise everything. Apart from that, there is something called columns, which we'll also learn a little bit, not in total details, but that also part of the course. Okay, so today let's start with axial members, and let us cover a part of axial members. What are axial members? Can anybody write what are axial members in the chat? Can anyone write that? What is an axial member? Members with only axial load. Okay. Anything else you want to add to that, Sridhar? You're very right. Members that can carry only axial loads. Okay. What are axial loads? Loads along the longitudinal axis of the member. All right. This should be 21. This is 20. Ah, good. Oh, not that. Okay. So, yes, it can experience only elongation and compression. Yes. So the point is, it carries only axial load. Okay, I can load it in any direction. I can load it in transverse direction. I can load it in its along its what's like a torque. I can give a torque also. I can give a moment also, but it will not take these loads. They are not designed to take this load, so they will fail under those loads. Okay, they will only carry axial load, so they will transfer loads from one part of its axis to the other part of its axis. Okay, so that's why they are called axial members, and they, as a result of carrying this load, they will either get elongated or get compressed along the axis. That's what they're going to show. What we have in syllabus is we have to learn, the main part of the course is to understand how the force deformation relationship for an axial member happens, how it behaves, the force deformation relationship. And we have in part to understand prismatic bars and bars with varying cross section. And we will do things for statically determinate structures and statically indeterminate structures. For statically determinate and indeterminate structure, both in linear zone. So we will all do all those things in the linear conditions, not in non-linear conditions. So linear elastic is considered. What happens under thermal stresses and what happens when you have stress concentration. And best part of the course is to understand strain energy for axial members, how to calculate strain energy for axial members, and how to determine forces or deformations. I would say forces given a deformation in an axial member, or deformation given a force in an axial member. Okay, using strain energy theory. We will do all those things. So this is a big part It is not small, but we'll try to cover it as soon as possible. So be with me with a lot of focus. All right, so while doing it, we will understand a few things here. The structural member may undergo various types of loads to axial, bending, transformation, and shear, but we are considering only axial. Okay, here it is only axial. As long as they stay within the linear portion of it, so linear elastic and linear strain deformation relationship, the axial deformation or transverse deformation, or its torque, shear deformation, they remain uncoupled. Okay. So when you have a general structure and your general structure, a 3D structure, and it can go both bending, it can go axial deformation, it can have torque also. In those cases, as long as you are within linear zone, you need not assume these forces are coupled. So you can assume that deformation due to axial load will be only along axial direction. Okay, they will not give rise to any kind of bending. That you are safe as long as it is linear. Okay. For nonlinear geometric, you have to assume it to be coupled. You cannot assume to be uncoupled. Then if it's a nonlinear and if there is a geometric deformation, then your bending can give rise to axial elongation, right? And your axial elongation can give rise to a moment, and then there can be a bending into the structure. So in those cases, it's no more a small deformation or no more a small rotation. It becomes large deformation, large rotation. Nonlinearity are generally of two types. One is called geometric nonlinearity and the other is called elastic nonlinearity. Okay. Geometric nonlinearity is nonlinearity due to large deformation. Okay, so that's different from elastic nonlinearity, where the nonlinearity is due to material being non-elastic. For example, rubber. Okay, where the stress-strain relationship is non-linear. So there is a slight difference here. So there are two kinds of nonlinearity that can come in a structure. One is geometric, one is elastic. Geometric means it's mostly the strain deformation relationships are nonlinear, and elastic means stress strain relationship is nonlinear. It can be either one of them. A material can be either nonlinear elastic, but linear in geometric. That means linear strain deformation relation can be used. That is possible. Also, it can be that a material is nonlinear geometric, but elastically it's linear. So stress strain relationship linear, but strain deformation relationship is nonlinear. That can also happen. But both the nonlinearity are outside the scope of our class. If any of you want to do a little bit of more study, please go ahead and do it. Okay, I'll be happy to help you with some notes, but you can always welcome to take up. Very interesting part of this, strength of very interesting part of mechanics is when it goes to nonlinear. Okay, there are two kinds of formulation that can happen in mechanics. One is called stress-stress formulation, where you know the external load, you find internal loads and the stresses. From stresses you go to strain, and from strain you go to deformation, and then relate the load, external load, with the deformation. This is one way of going through it, right? And what you need is you need a force deformation equilibrium equation to get this. Then you need material models. So equilibrium equation. So free body diagram gives this one. Equilibrium equation gives this one. Material models gives you strains, and then strain to force deformation relationship. Strain to deformation relationship gives you strain deformation. And from that you can get the relationship between force and deformation. The other way out is called deformation based formulation, where you know the deformation. Okay, you know deformation, and from there you go around and find out how much the load is there on the structure. It's like forensic study. You know what has happened, and you need to know why this has happened. So how much load has come to the structure. Okay, so that's this one is a straightforward direct formulation, and this is called inverse formulation in mechanics. Let's go ahead to axial members now. What are axial members? Where do we use axial members? Axial members are widely used in mechanics, very much. They are used in bridges. As you can see, there is a stay cable. There is a suspension bridge where the suspension strings are made up, assumed to be axial members. Then you have a cable stayed bridge where the cables are designed to be axial members. They are generally cables. Cables cannot carry anything apart from axial load. It can only carry axial load under moment and all. It cannot show any kind of response. Apart from that, you can use springs. We design a lot of springs in mechanical engineering. Those springs are generally members that carry axial loads. Then truss members and columns. These are all designed to be axial members. Okay, so there is a lot of application of axial members, and therefore it forms a very important and interesting study of mechanics. Now let us define what we want to do. Let us develop the equations. We know an axial member, right? Let's consider an axial member like this here. The axial member has a load P and its cross-sectional area is A. So this is a prismatic bar, okay? This is called prismatic bar. It's because its cross-section is not changing. Its cross-section is constant all through. All right. Prismatic bar, its cross-section is straight all through, the same all through. So A is not changing. It's constant. Therefore, we know that the stress along the structure is going to be constant. It's not going to change because A is not varying, neither P is varying. And then stress is given as normal stress is given as P by A. Now looking at the strain, normal strain, how do you find normal strain? So strain is going to be epsilon x is going to be du by dx if given u. If you know u, then it is du by dx, right? Which for this kind of member, we can write it as del u by del x also, because u is not changing heavily here, it will change only linearly, and it's a prismatic bar, which can be written as delta by L, okay, at L. At x equal to L. Okay. This is L and this direction is x. So at x equal to 0, what are the boundary conditions that I have? Let us write the boundary conditions now. For this member, we have the boundary conditions. At x equal to 0, u equal to 0, right? At x equal to L, u equal to delta. We don't know what is delta, but that's what we are naming it to be delta. What we are going to do now, we know epsilon x at L is going to be delta L by L, and sigma x is equal to E into epsilon. This comes from the constitutive relationship. So let us write that constitutive relationship. Gives me this. Okay, now I can write sigma x. I can replace those values. I can write sigma x equal to P by A because sigma x is constant. So at this point also sigma x is P by A. So I'm assuming it to be P by A is equal to E delta by L. So I can relate delta and P directly, which I can write here itself. This gives me P by EA is delta by L. Delta by L is equal to P by EA. Okay, this is the formula for axial member deformations in axial members. Let's go ahead. So what we got is you have an axial member like this with a prismatic axial member. So with a constant cross-sectional area A, and you after you have put a load P, and after the load P is given, it has elongated a little bit because the axial load is tensile load, right? So the elongation is delta, total elongation at the end. C is delta. Sigma x average is P by A, epsilon x is delta by L, right? And therefore sigma x equal to this, by constitutive relationship, you can write sigma is equal to epsilon into E, and you can combine these two, finally you get delta equal to PL by AE. Remember this formula, PL by AE, okay? This is a very nice formula, you can remember it, it will be useful. E is the Young's modulus of the material with which the member is made. How do you go? Again, same thing. This is the direct formulation. So you know P, and from P you can find the internal force. So anywhere you take internal load, it will be P. So the stress is constant all through. So we can write it as the stress is N by A, where N is the internal load. Okay, N is the internal load. So equilibrium equation gives me. So if you remember, I have shown how do you go it. So you go by equilibrium equations, then material model, then strain deformation, then force deformation relationship, right? So if you go by that formulation, So this is your internal load, and from that you get equilibrium equation is P equal to N. So the internal load is N, and stress is given by internal load divided by A, so that becomes P by A. And Hooke's law is used to find the strain deformation relationship. So this makes sure that system is linear. Okay, and then the strain deformation relationship comes into action. Strain relationship and kinematic relationship, which is called strain deformation relationship, is this, which when you relate, get delta equal to PL by AE, where P is the external load, L is the original length of the axial member, A is the cross-sectional area. Delta is positive for elongation and negative for reduction in length. Okay, so let me ask you a few questions. One is, I have a member like this, okay, and I've given a load P here, and this is my length L. How will its deformation look like if I have to plot U? Let's say U with respect to P. We know, or not U, right? We are writing it as delta or not delta. U is fine. So U, we know that U equal to delta U at L is PL by AE. Now A is constant, E is constant for the same material, L is also constant for the member. So it's going to go like linear, right? Linear curve. This is my delta. Okay. Now along X, how it's going to look like? U of X. P is same, so you take a cross section here. P is same, right? Only thing L is changing. Again, you take a cross section. P is same, L is changing. Again, you take a cross section. P is same, but L has changed, right? Because L will be up to this much only for this, up to this much for this, to this much for this, right? So it will be a function of L, and L is changing linearly here. So U is going to change. How do I show it? Yeah, U is going to change like this. It's 0 at this point because this boundary condition U is 0, and it will go like this, and it will come here. This is delta U of L, and this is U of X at any point. Okay, that's how it's going to look like. Now, one challenge for you is, instead of that, if I have the load like this, but I give a load here, P, how will its deformation look like, the curve? U of X. Yeah, anyone?
Sir, a triangle, sir? A triangle.
Triangular in the sense there can be a lot of triangles, no?
Like it will increase and then decrease, sir.
It will increase and then decrease. Okay, anybody else? It will increase,
sir, it will increase,
then
and then it will be discontinuous, and then like reverse it will decrease.
Okay, let's look at it. Okay, what is the deformation here? Deformation there is 0, right? And then till here to here, from here to here, the deformation is going to go linearly up, right? So it will go linearly up. What will be the value here? The value there is P L by 2 by AE, right? Isn't it? It will be P L by 2 AE is the deflection there at X equal to L by 2. What will be the deformation after that? At this point, at this point, at this point, at this point. So let's take a cross section here, okay? Let's take a cross section here. So that's my cross section. And what is the load here? 0, right? There is no load on that part, right? Load is acting here. Therefore, deformation is 0. Right? So there is no deformation at that point. But what happens? This point has already moved by this value, delta value, this point. So these points will move by delta value, right? So at this final point, what is the deformation? Again, the same delta value. And therefore, this deformation is going to be like this. This is also delta equal to E L by 2. Clear? Any doubt here?
Sir,
Yes.
sir, in this picture, like when the force P is acting towards right at this point, sir, it seems like this force is trying to elongate the part of the rod which is to the left of the point, sir.
Yes.
But won't it seem like the force P is trying to compress the other? Oh, okay. So there's no okay. I get it, sir.
Yes, there is no boundary there, right? So it will not compress. That sky will move like a rigid part, right?
Yes, sir.
And therefore, whatever deformation you have here will continue to the whole part. Okay, there is no deformation that will add up. I hope that's clear to all. Okay, if you have no questions, I'll go ahead. Any question?
No, sir. And one last thing, sir. Like in the previous case, are these two graphs same or they're different, sir?
Can you see they're same, these two graphs?
Yeah, they should be same, sir.
Why they
No,
should be same?
not that, sir. Not that, sir.
Then?
The graph on the right to the, I mean.
No, this
first
graph, this graph is P delta curve. Okay, this is a different graph, P versus delta. So when you change P, if you change this P value here, how will the delta curve look like? And this U is along the axis, how it's changing. So like bending moment diagram you are draw, no? Similar kind of thing. Each location will represent the deformation at that location. So this represents deformation at this point. This deformation is at this point. This is the deformation at this point, and this is the deformation at that point. Like bending moment diagram or CFL diagram you draw, we are drawing the deformation diagram here. Similarly, here also for this second picture, the deformation at this point is this 0, and so on. So deformation at that point is this. This is the deformation for P point where the load is acting, and the same deformation for the end point. Okay, so you can actually write this is as U of x here, and this is only x. Okay.
Yes,
Right. So now let us understand this in a little greater way, a little bigger way. When you have many loads, what happens? So there are multiple loads, okay? Multiple loads, but the cross section is same. The cross section is not changing. What you do in that case? Remember, we said that the internal stresses and strains depends not only on the external load, but it depends on the internal formation of the loads, right? So you have to calculate internal loads from the external forces that you get. Because this one, if I have shown you, the derivation actually depends on n, not on p. But since n is equal to p, we write it as p. So now let us consider a member. This is again an axial member which fixed on one side, and you have various loads at point B, C, and D. You can see at D there is a tensile load, at C there is another tensile load, but at B there is a compression load. Okay. What we have to do is we have to find internal forces first, right? We have to find the deformation of the whole structure. So what we do, we need to find stresses at various locations, then strains at various locations, and then from that we can get the deformations at various locations. That's the way we go, right? We first find stress, then from that we find strains, and from that we find deformations. So we go ahead that way. So let us take section at this point. There is one section I'm taking. I take another section at this point, and I take another section at that point. So this section that I have at the lowest point is easy. So this is the part I can take. So that part has PD on the bottom side. So there will be PD on the upper side. That let us call that as N3. So N3 is equal to PD. Okay. Now let's take the second cross section. Let us look at this section cross section. And you see now again there is a PD at the bottom here, but there is another PC here, right? Here at the C point. So N2 is going to be opposite to these two. So N2 is going to be PC plus PD because they're on the same direction. So N2 is equal to PC plus PD. Okay. Now the other cross section that I have here, let me take that, and what I will get another cross section I took, and then there is N1 is the internal force. So N1 is going to be, this is negative side, right? So minus PB plus PC plus PD. Okay, that's my N1. Now, what we have to do is we have to find the total deformation of the structure. Now, total deformation of the structure, we know that the deformation is going to linearly increase from here, come to a value at this point, right? Again, then it will change linearly and come to another value at this point. Again, it will change linearly and come to a value this point. So if I know this value, and this value, I can find the total deformation, because the portion here will have a shift, rigid shift, because of the deformation here. Similarly, portion here will have a rigid shift because of the total deformation up to this point. Okay, clear? Because there are no loads acting here. So let us find what is the delta 1 deflection. So delta 1 deflection is due to N1. What is N1? N1 is, this is my delta 1 deflection. Okay, this is my delta 1 deflection. So this is L1 and N1, it will be related to, it will be N1 L1 by EA. Remember that PL by EA. So N1 L1 by EA is my delta 1. Delta 2 is N2 L2 by EA, and delta 3 is similarly N3 L3 by EA. So deformation at this point, B point, okay, is due to the load that is acting at B point and the area with and the length between A and B. The length between A and B is L1. So I have L1. This internal load, or the force that we have between A and B, is N1. We have found that here. And divided by EA, the rigidity of the material will give me deformation. Similarly, the other two. So the total deformation is going to be delta 1 plus delta 2 plus delta 3. Okay. So that's your total deformation. So total deformations can be written as, provided they are along the same direction, is given as summation I equal to 1 to 3 Ni Li by Ei Ai. Now, why did I write Ei Ai? If Ei Ai are not constant, they will be also inside that as an ith variable. Okay. For example, I can change the material. I can have first part as a steel material, then I can have brass, then I can have copper, right? I can change the cross-sectional areas also. So this becomes a general formula for the complete system. Okay, clear? This is drawn and explained in a better way if you do a axial force diagram of the system. So between A to B, you have a force that is called PB, right? And from, why PB? What is this? Okay, this small change is PB, right? So if you draw from this side, from here to here, it is PD force, because PD force is only acting here. This is my PD force. Then it's added up by PC. So this is PD plus PC, then goes straight. There is no load here. Then there is a negative PB, so it comes down and goes like this. So this is my axial force diagram. And this is the diagram divided by the area. If your area is constant, then it will be similar diagram with only scaled by A. And your total deflection will be this, and you add up. So it's in a better way explained using this diagram. Now, can you draw the deformation of this? So deformation, you can see the first deformation is, depends, all are positive, right? All are positives, all going to be tensile, because all the forces seems to be positive. So it's going to look like this, then probably this, then probably this. So the slope will change based on how much load you have here. Okay, having said that, now you can relate the force deformation relationship in a better way using spring as your example. What you do is, you know that deformation is given by PL by AE. So P is equal to EA by L into delta. Okay, and we know force to deformation is related with something called stiffness of the material. For springs, we tell that spring has a stiffness K, which means that if you give a load P, the deformation is going to be P by K. So that's what we call as spring stiffness K. So spring P is equal to K into delta, where K is the spring stiffness. Okay, so that stiffness is given for an axial member is written as EA by L. So for an axial member, the stiffness is EA by L, and flexibility is opposite of stiffness. It's an inverse of stiffness, in which case you have been given load and you have to find deflection. So deflection into load, the deflection is equal to force into flexibility of the material. Okay, so that comes out to be L by AE for an axial member. So when we say what is the stiffness for an axial member, you have to write it is force per unit deformation, and that is given as EA by L. Now for in matrix structures also, we take inverse of stiffness matrix to get my flexibility matrix. It is most of the time it is very easy to find stiffness matrix for the materials and members, or a complete given structure with lot of members, and then you can find deformation using your equation of statics, that is x, which is can be a vector, is K inverse E. Okay, where K inverse can be F. Members that have different cross sections of area. Okay, so let us consider again prismatic two cross sections, prismatic cross sections. One of them is of higher area of cross section, the other one is of a lower area of cross section, right? And they are being given compression force at PA and PB at A and B locations respectively. Okay, so first thing is the cross section here is constant from A to B, and the load is also constant. So I can take any cross section and find the internal force N1, and that's going to be minus PA. Okay, minus because it's negative, it's compression. Okay, because the load is compressive. So the deformation is going to be delta equal to, where is this deformation? This deformation at this point, right? At B point, the deformation is going to be N1 L1 by E1 A1 because of this portion of the load and the material. Now for delta 2, which is at C point, what we have to do? We have to calculate the internal force at N2. The internal force at N2 is N2 L2 by EA2, and which calculates to be minus PA plus PB, which you can calculate, and then you can calculate deformation also. So the total deformation is delta 1, the deformation due to this portion, and the deformation due to this portion. So N1 L1 by E1 A1 and N2 L2 by E2 A2. And that can be written in a summation sign as I have shown, and this is the final summation sign. Delta is equal to I equal to 1 to N. If you have N number of this kind of discontinuities, N1 Ni Li by Ei Ai. Okay. This can be better written as Ni by, you can see this is the stiffness of each of the members, right? So this guy, this whole structure can be represented as connection of two springs with different stiffness. One of them is E1 A1 by L1, the other one is E2 A2 by L2. So this is, let's say, E1 A1. Now this will be E2 A2 by L2 because this is connected to the fixed end, and this will be E1 A1 by L1. Okay, so your final deformation expression comes out to be this one. All right, Ni by Ki. Ki is the stiffness of each of the separate springs. So whereas what we are doing, we are changing the axial members to a stiffness spring because it becomes easier for us to understand springs from mechanical engineering perspective. Few terms very important for you to understand. One is EA is called axial rigidity of the member, EA by L is called stiffness of the member, and L by EA is the flexibility of the member. What is stiffness? Stiffness, I hope you know what is stiffness. Stiffness is force required for deformation. Okay, it's represented mostly as KII, where one I, Kij, I is the location of load, the position of load, and J is the deformation location. Okay, flexibility. Sometimes we call, structure is so much flexible. Sometimes we call structure is very stiff, right? When you say it's very stiff, we mean that it has less deformation, right? It's more towards rigid. And when we say it's very flexible, we mean that it's far away from rigidity, right? So it's very flexible. It can bend very quickly. So it is opposite inverse of stiffness. Okay, it is inverse of stiffness or inverse of K matrix. So this is actually, if you give a new deformation, what are the forces that are being generated? Force generated for unit deformation. Okay, so this is again is Fij. Inverse. Right, here is another problem for you to go through. You can go through this problem. They are not very difficult problem. As I've discussed, you have a bar member with a different cross-sectional area, but constant for its own section, right? So you have two loads given, one is at B, one is at C. The load at B is 75 kilonewton, the load at C is 45 kilonewton. There is another load at D, which is 30 kilonewton. Load D at D is tensile, load C is compressive, load B is again tensile. Okay. So if you draw the load diagram, the load diagram will look like D is 30, so it's positive 30. Then there is a negative 45, so it comes down, so it becomes negative 15 here. And then here it's positive 75, so it goes up again and then like this, so up to 60. So the load internal force here is 60, here is negative 15, here it's positive 30 again. Okay. So now you know N1 is how much, N2 is how much, N3 is how much. N3 is this part, N2 is this part, N1 is this part. And then you can add them delta 1, delta 2. You can find delta and you can add delta 1 plus delta 2 plus delta 3 to find your total deformation. And I'm giving you a duty to draw the deformation curve. Okay, can you please draw the deformation curve? So the whole calculation is shown here. You can see. So the total deformation is 111 into 10 to the minus 5 meter. So you find delta 1, which is N1, A1 by E1, delta 2 and delta 3. So the calculations are shown here. And then you can find delta at T. So it will be total of delta 1, delta 2, delta 3. Please note that delta 2 has come out to be negative. That means there is a compression in between because of the compressive force here, compressive internal force here. Okay, not because of this compressive force, because of compressive internal force. This compressive may not give rise to your compression internal force because it depends on the other two forces B and D. Okay, I will. So let's stop here. No, let's not stop here. Let's take another example. In the last two examples, we saw a prismatic bar with a constant cross section. Then we saw a stepped bar, but the cross section had been constant for a certain length. Okay. In this example or in this problem, what we have is the cross section is constantly changing. You can see the constant. It can also change like this. What happens? What you should do? How do you find a deformation in a structure whose area is constantly changing? Right. One way of doing is very simple. Where is that? Yeah, one way of doing is you have this formula. This formula is there. Now what we are doing is we're telling that the cross section is constantly changing. So L is very small in that case, right? Li is almost like del L, right? And AI is also changing, becomes a function of X in that case. So what you do in that case to find delta, this becomes continuously changing in a limit, right? So this becomes an integral, 0 to L. The same thing I'm going to show you here. So what happens is you consider a small cross section at a distance X, and that is dx. Okay, dx length, and the cross section along this dx length is assumed to be constant, not vary. because this is a very small dx, right? And the deformation that happens between these two due to this internal load is del delta, del of delta deformation. If you take this, free body diagram of the section here, the internal force that is acting here is, let's say, nx. We don't know what is nx. We have to do all the balance to find nx, right? But since we don't know px, we don't know nx also. So if this is the cross section, I can find that the cross section here, this is nx, there, this is nx, right? And the deformation that has happened is delta dx, because this is very small. A is also assumed to be constant. So sigma, the stress that is acting in this material, is going to be nx by ax, and the strain in the material is d delta by dx, right? Dx is this length, and delta d is the elongation that has happened. So this is the strain. So therefore, d delta, if I use that formula, is going to be PL by AE. P is my nx, A is my ax, and L is dx, because this is the small area, and E is, you can assume to be ex, or it's constant, doesn't matter. It depends on what is given to the. So the total deformation is going to be, you have to integrate it from 0 to L, right? So we just integrate to 0 to L. Total deformation becomes integral 0 to L d delta. That, if in place of d delta, now you replace this whole thing, it comes out to be nx by Ea dx, right? This is my, now assume A to be constant, A of x to be A, okay, and P at the boundary, free end. Then what we have in nx is equal to P again, because in that case the member looks like this, right? You have a constant cross section and with a point load P here. This is my A. So this one becomes delta equal to integral 0 to L. Nx is P now, dx by AE. So it becomes PL by A. That is what we derive. Okay. So this integral formula is a is a classical formula. It can be used for any kind of cross section that you have, right? It's more general in that sense, or any kind of E that you have. If E is also changing, that can also come within the formula. Yes. Any question here?
Sir, this assumption which we took is that we took a particular case, and I correct, sir, like we didn't solve for this, right? Like actually we took nx is equal to p is obvious because like p is constant, so nx will be a constant, but ax according to this question will vary, no sir, like with x.
No, what I'm telling is this is a general formula, okay? This is a general formula. You can use it for any member. So there is a problem here solved also. Yeah, here, yes, here. Okay, so this is a constantly changing cross section, a conical structure. How do you find deformation at the tip? So in that case, you have to use that formula that you have, integral. We'll come to this problem in the next class. Again, you have a constantly varying cross section here also, right? How do you find the deformation at this point? Because the formula that we have, PL by AE, assumes a constant cross section. The cross section is not constant here. It is constantly changing. So in such a case, you cannot use your PL by AE formula. What you have to use is an integral formula, differential formula, which is given by this one. This, what I have done, is for a check. Okay, for a check to see that whether this condition gives us back to our PL by AE formula or not. So what we do in that case, you assume it to be a rigid bar, a prismatic bar, right? So your A has to be constant. So if A is constant, it comes out of integral. E is constant, it also comes out of integral. And if you put a load at the free end, then your load is also constant. That means your free body diagram, internal forces P all through. So that also comes out of integral. What do inside integral, what do you get? Only dx. So integral of dx over L, 0 to L, is again going to be L, right? So it becomes PL by AE. This is a check for this formula. Okay. Is it understandable?
Yes, sir. Yes, sir. Yes, sir. Thank you. Thank you.